Hey everyone, and welcome to this explainer on large tabular models. For the past couple of years, the whole world has been absolutely fixated on large language models. We've been completely captivated by AI that can write our emails, draft essays, and chat with us like a real person. But while we've all been a bit distracted by these chatbots, a massive shift has been happening quietly in the background. A shift that's targeting the actual financial and operational backbone of the global economy. So let's dive right into this.
I love starting with this brilliant metaphor from AI governance expert Ganthy Ganardhana because it perfectly captures the fundamental limitation of our current obsession with language models. Language models are absolutely incredible at poetry, prose, and conversation, but asking them to reliably forecast a financial quarter or parse a massive relational database of transactional logs, that's just not what the system was built to do. Honestly, if you've ever tried asking a chatbot to do your taxes, you know exactly what she means. And that limitation is exactly what's driving a massive technological pivot.
So here is our roadmap for today's explainer. We'll start with the enterprise AI blind spot, look at what large tabular models actually are, and dive into diffusion versus autoregressive methods. Then we'll see how they're replacing traditional machine learning, transforming banking and operations, and finally wrap up with governments in the tabular era.
Section 1. The Enterprise AI Blind Spot. Structured versus unstructured data.
Okay, so it might surprise you to learn that 80 to 90% of enterprise data is totally unstructured. Think of your endless streams of emails, Word documents, and chat logs. That is the playground of large language models. But that remaining 10 to 20%, that structured data, is the actual treasure chest. We're talking spreadsheets, relational databases, transaction ledgers, sensor readings. While unstructured text makes up the bulk of the data, the highly structured data found in these ledgers is what actually serves as the operational backbone for forecasting and decision-making. That smaller percentage holds the literal core value of the enterprise.
Section 2. What are large tabular models? Specialized foundation models for structured data.
Because asking an LLM to read a spreadsheet is wildly inefficient and honestly quite risky for a business, a new class of specialized models has emerged to solve this exact problem. So what is an LTM? Well, large tabular models are foundation-style models trained specifically on vast amounts of tabular data. Instead of predicting the next word in a sentence, they're designed to directly ingest structured data sets, rows and columns, for prediction, forecasting, and pattern discovery. And the best part? They do this without the heavy manual feature engineering that data scientists usually have to perform. If you've ever spent weeks cleaning up data for a machine learning project, you know why skipping manual feature engineering is a total game changer. LTMs are essentially trying to do for enterprise spreadsheets exactly what LLMs did for natural language.
Section 3. Diffusion versus autoregressive methods. How AI actually processes numbers.
To truly understand why this matters, we need to get into the technical weeds for a second and look at how these models process data mathematically. This is where the limitations of LLMs become glaringly obvious. Traditional language models use what's called autoregressive tokenization. If you feed a table into an LLM, the model literally linearizes the table rows into text sentences. It treats continuous numerical values like discrete sequential text characters, so it literally reads the number 1.23 as the token 1, then a completely separate token for the decimal point, and then the token 23. It's incredibly inefficient. It's kind of like teaching a toddler math by having them read the dictionary. Generating that one simple number requires multiple expensive forward calls. Plus, the multinomial objective of an LLM completely fails to approximate continuous mathematical distributions. It's just a really bad way to process numbers.
So how do LTMs fix this? Researchers developing models like LaTable at the University of Cambridge use a completely different architecture called mixed-type diffusion. Instead of predicting the next discrete token, LTMs use a denoising process. Essentially, they smooth out the mathematical noise to zero in on the true signal. This allows them to treat numerical data directly as continuous variables. And what about categorical data, like the word female or male in a column? Well, LTMs actually map that text via LLM embeddings into a shared mathematical hidden space right alongside the numbers. Because of this diffusion architecture, LTMs are incredibly fast, predicting across all features simultaneously rather than painfully generating one text token at a time.
Section 4. Replacing traditional machine learning. Speed and the power to predict.
So how does this new diffusion architecture stack up against the traditional machine learning techniques that data scientists have relied on for years? Well, for decades, traditional ML required bespoke, manual feature engineering for every single new dataset. It was incredibly tedious and time-consuming. But large tabular models, much like the Nexus model developed by Fundamental, completely changed the game. They are pre-trained on billions of diverse tables. They innately learn the generalized patterns of how data behaves in rows and columns. Because of this, LTMs instantly apply this pre-trained knowledge to new datasets with zero manual preparation. They just transfer the knowledge instantly.
And the performance leap we are talking about here is absolutely staggering. 3 seconds. Recent technical reports on models like TabPFN 2.5 show that LTMs can produce highly accurate results on classification problems in under 3 seconds.
When you compare them head-to-head, this represents a monumental shift. Traditional ML requires hours of hyperparameter optimization and complex drift monitoring. It's highly bespoke with almost no ability to transfer learning from one spreadsheet to another. LLMs, on the other hand, deliver precise predictions in seconds and completely eliminate manual data prep. They offer what's being called drop-in intelligence. You don't need a massive, expensive greenfield machine learning program anymore. You literally just bring the model directly to the data.
Section 5. Transforming banking and operations, deploying LTMs in high-stakes industries.
Let's zoom back out and look at what happens when we unleash this drop-in intelligence capability on the massive data repositories of the financial sector. The banking industry is perhaps the most immediate beneficiary of LTMs. Why? Because major banks operate on petabytes of structured transaction records. The scale is just massive. LTMs offer an incredibly fast deterministic way to model credit risk and detect fraud across millions of rows of data. They can handle regulatory compliance, forecast customer behavior, and optimize really complex pricing models. And unlike LLMs, they deliver the precise, auditable numerical outputs that highly regulated industries actually demand.
And here is the real practical magic of LTMs. Because they operate natively on tabular data, these models plug seamlessly into the existing business intelligence dashboards, SQL layers, and ELT pipelines that enterprise teams already rely on every single day. There's no massive rip and replace of your IT infrastructure required. The AI meets the business user exactly where they already work.
Section 6. Governance in the tabular era, accountability for automated forecasts.
Integrating such powerful, invisible infrastructure into our core operations brings us to a really critical warning about AI governance. As Gayanthi Gunwardena points out in her research, we must be incredibly careful to avoid what she calls the illusion of competence. We naturally, but mistakenly, assume that an AI that speaks well and can write a brilliant email can also reliably forecast a financial quarter or price alone. Fluency in conversation does not equal competence in operational decision-making. Now, LTMs correct this risky assumption by specializing in the math, but they introduce new, serious risks of their own.
Because LTMs are decision-shaping systems that won't feel like AI to the end user, they're basically just going to look like numbers updating on a dashboard, we absolutely must introduce new forms of accountability. I mean, how do we explain an LTM's prediction? If an LTM makes a hidden correlation based on billions of historical data points, how do we prove the logic actually holds up? We need mechanisms like statistical confidence intervals. For instance, an LTM stating there is a 95% probability a value falls between two numbers, so we can step in and block or veto decisions that exceed our risk threshold.
Which leaves us with one final, absolutely essential thought. Thank you so much for joining me for this explainer. As large tabular models silently and efficiently optimize our financial systems in the background, making split-second decisions on credit, risk, and fraud, when the algorithm eventually makes a mistake, who ultimately bears the responsibility?